Alright, we're looking at the conservation of energy in gravity problems. Alright, and the example we have here is we have a roller coaster and we have a certain amount of potential energy up the top, and that gets converted into kinetic energy when it goes all the way down to the bottom. So if we've got a height of 5 meters and we're considering the bottom 0 meters, then the change in kinetic energy is going to be equal to the change in potential energy. But the most important idea with conservation of energy is that the initial total energy before an event is equal to the final total energy after the event. And the equation they have down here is they've got a half mu squared, so that'd be the kinetic energy initially if it's got initial kinetic energy. This is the initial potential energy, and then they've used up all the potential energy and they've got some sort of final energy here. But we can make it a bit more general if I'll just get rid of this equation out of there for a second. So let's ignore that. Let's say that we're about halfway along this roller coaster, and we've got a height of h2 and we had h1 up here. Okay, so then this initial height would be h1, and then our final total energy would include another potential energy of height 2. So that's a bit more general, so you could actually measure what all the energy is. So final total energy, initial total energy equals final total energy, and but this is also assuming we're not losing any energy to heat or sound or things like that. So let's move on to some examples. So we have a boy at the top of a roller coaster falls through a vertical distance of 20 meters. What is the final speed of the boy if his initial speed was 0? So we start off by saying that his initial energy is equal to his final energy, and he starts off with potential energy, and that gets converted to kinetic energy. So he has mass times gravity times height is equal to half times mass times v squared. So they didn't give us mass, so normally they give us a mass and a height if they want us to calculate potential energy, but because they're looking for final speed, and we know that potential energy equals kinetic energy, or at least the change in potential energy is equal to change in kinetic energy, then those m's just cancel out from both sides. Okay, so now we want to isolate v. So v is going to become, if we times both sides by 2gh, and we can take the square root of that. Okay, so now we can substitute our values in. So velocity is equal to the square root of 2 times by 9.81 times by 20. And that becomes 19.8 meters per second. And because they asked for speed, we don't need a direction. Okay, so they've slightly made this a bit more complicated. So they've given him an initial speed. So the initial energy this time still equals the final. But this time we've got mgh plus half mu squared equals half mv squared. So again, all these masses cancel out, and then we can times both sides by 2, so we get 2gh is equal to, and my words just decided to stop responding for a second, plus u squared equals v squared, and we can substitute the numbers in, so we get v is going to be equal to the square root of 2 times 9.81 times 20, like we had above. That's also going to be equal to plus 5 squared in there. And therefore v, our final velocity, is going to be equal to 20.4 meters per second. Okay. So the same boy in question 1 above has a mass of 40 kilograms. What was his potential energy when he had fallen 10 meters vertically? So we've got our boy on a ramp like this, and this height here was 20 meters, and now he's at this point here, which is 10 meters. Okay, so we can actually just calculate his potential energy here, which is going to be equal to 40 times by 9.81 times 10, and that's equal to 3,924 joules. Okay, so that's his potential energy at 10 meters, so he's still 10 meters above our endpoint. Now, what was his kinetic energy when he had fallen 10 meters vertically? Well, we can say that the change in kinetic energy equals the change in potential energy. So we could go through the maths and work out what his potential energy is at the top of it, but we can say that it's just going to be twice this number here, because he's just gone through, he's fallen half his height. So that means that the change in potential energy is going to be this as well. So when he gets all the way down the bottom, his total kinetic energy is going to be 2 times this. So that means that halfway, his kinetic energy is equal to 3,924 joules also.